The 2025 hurricane season saw an unusual concentration of power. Three separate storms in the North Atlantic reached Category 5 strength, leaving behind a level of destruction that tied nearly century-old records. Yet, while the destruction on the ground felt record-breaking, NOAA's global temperature data told a different story. 2025 was only the third warmest year on the Earth's surface. Despite that third-place ranking, 101 named tropical cyclones formed globally, which is significantly higher than the 1991 to 2020 average. Surface air temperature is only one part of the equation. It doesn't represent the total energy being trapped within the planet's systems. To find the thermal energy that actually fueled these storms, we have to look past the atmosphere and search underwater. The global ocean acts as the Earth's primary heat sink, absorbing 90. This chart shows the heat content in the upper 700 meters of the ocean. While surface temperatures fluctuated, the ocean heat content reached a record peak in 2025, marking the fifth consecutive year of record-breaking heat storage. The ocean is absorbing and storing this energy, acting as a massive heat sink for the entire planet. Much of this excess heat doesn't stay on the surface. Instead, it enters the deep ocean cycle through the churning waters of the Southern Ocean. This is driven by the physical pump. In polar regions, surface water cools and becomes denser. As the water grows heavier, it begins to sink. As this dense water sinks, it physically drags surface heat and dissolved carbon dioxide down with it, moving that energy into deep currents that travel through all the world's ocean basins. Scientists track this process using instruments like this Argo float, which dive into the water column to measure temperatures at depths humans can't easily reach. This movement effectively hides the heat from the atmosphere, burying it in the deep ocean for decades or even centuries. While the majority of that heat remains in the upper 700 meters, polar amplification is now driving warming into intermediate depths, between 500 and 1,000 meters down. So, what happens to the ocean itself when it absorbs this much thermal energy? The result is a physical phenomenon known as steric sea level rise, or thermal expansion. As water heats up, molecules gain energy and spread apart. Because they require more volume, the sea level rises. This physical expansion of warming water accounts for about 1/3 of the global sea level rise observed over the last century. The ocean isn't just rising because it's being filled with meltwater. It's rising because the water already there is physically taking up more space. This warming at intermediate depths is now attacking polar ice from below, accelerating the rate of melt even in regions away from direct sunlight. According to the IPCC, these changes operate on a different timescale than human planning. The heat the ocean has already absorbed creates a delay in the climate's response. This is thermal inertia. Even in scenarios where we stop all greenhouse gas emissions by 2050, the heat already stored in the system will continue to drive thermal expansion for hundreds of years. Our past carbon emissions have already committed the global coastline to a cycle of expansion and recession that will continue for centuries. This expansion is already impacting the daily operation of coastal cities. Coastal communities are now choosing between three main strategies: accommodate the water by flood-proofing infrastructure, or advance by building new land seaward. The most common choice is to protect, relying on hard infrastructure like these concrete seawalls and surge barriers to hold back the rising tide. But as sea levels continue to climb, some communities will face the most difficult choice: coastal retreat, or the permanent relocation of people away from the shoreline. The ocean shielded us from the immediate impacts of a warming atmosphere, but as that reservoir fills, coastal communities are now facing a sea that is physically larger and more volatile.